And good evening, High Legh. It's wonderful to be back here again. So here we have a couple of short talks. The first one is just a second, and as you can see from the subtitle, I'm asking what a second is. Perhaps you already know, but what a second is, and essentially why we need leap seconds. So I'll be looking at a little bit about time and motion, asking what a second is, how a second is defined, and just to give a little bit of context, I'll be asking what can actually happen in 1 second. But most of this talk is about what's happening to the rotation of the Earth. The Earth has been slowing down for a few decades, and I'm going to be talking about why that is occurring. And what are the consequences of the fact that the Earth has been slowing down for quite a few decades now? And finally, why we actually need leap seconds, or do we need leap seconds, and what happens when they are inserted into our clocks. So, how does humans think about time? If you really think about it, in a sense, we don't understand what time is. But we do understand that things move. And therefore we can define time by the motion of something. It's always the motion of something that gives us the concept of time. So of course, for quite a few millennia, the idea of time is dictated by, for instance, the fact that the sun appears to move in the sky, and hence we can build ourselves a sundial, and that gives us a way of recording time. And as well as looking at time during the day, we can also use other astronomical phenomena, such as, for instance, the phases of the moon, to tell us how time is going from one day to the next over the period of a month, and then it cycles around. So we have always, for historical time, for prehistoric times, we've used astronomical events to give us an idea of the passage of time. And if we ask ourselves what is a second, perhaps you think that's a totally trivial question, because we know that the Earth rotates on its axis once a day. And we have conveniently split the day into 24 hours, and we've split an hour into 60 minutes, and we've split each minute into 60 seconds. So we've got 24 hours, each of which is 60 minutes, each of which is 60 seconds. So clearly 1 second is simply that fraction of a day. There are 86,400 seconds in a day. That number, 86,400, is going to crop up a few times in this particular talk. So if that's the definition of a second, it's just that fraction of a day, then simple. That's all there is, presumably. That's the end of the talk. Well, sort of no, because this talk is going to actually go for quite a few thousand seconds. So let's have a look at how the Earth moves. The Earth moves around the sun in an ellipse, and because of the nature of how objects move in ellipses when they orbit either a planet in the case of a moon or the sun in the case of a planet, it was figured out by Kepler and Newton exactly why the planets move the way they do, but the bottom line is planets sweep out equal areas in equal time. In other words, if you think of a line joining the sun to a planet, then these two blue almost triangles here are basically the same area. So you can see that when a planet is a long way from the sun, it actually doesn't move very fast, whereas when a planet is closer to the sun, it's moving faster, and it ends up producing these equal areas. So the Earth's speed, the speed at which it is moving around the sun, varies during the year. Now, of course, that's an exaggeration. The Earth's orbit isn't as elliptical as that particular cartoon would indicate, but the principles are still the same. When we're closer to the sun, which we are in January, the Earth is moving a little bit faster than when it's at its greatest distance from the sun. But the speed at which the Earth rotates doesn't change that much during a year. So in terms of where is the sun in the sky, you can perhaps see that if the Earth is turning at a particular rate, but it's not going round the sun at a constant rate, it's going slower and then faster, and then slower and then faster. The position of the sun in the sky at a given time of day is going to change. And if you photograph the sun, I've never actually tried this myself, but if you've got the patience to photograph the sun at a particular time, it doesn't have to be noon, but let's just pretend that we're going to photograph the sun every day or every week at a particular time of day, let's say noon, then what you end up with is this figure of 8 pattern. Now, it's perhaps no surprise to know that the sun is higher in the sky during the summer than it is during the winter. That, I guess, is no surprise to anybody because of the tilt of the Earth, the 23.5-degree tilt. In northern summer, we're tilted towards the sun, and so it appears to be higher in the sky. So if this was taken from the northern hemisphere, which it was, then the position of the sun in June is at the top here, and the position of the sun in December is at the bottom. But what is a little bit more surprising is the fact that if you take a picture of the sun at, for instance, noon every day, it doesn't give you a vertical line. You tend to think of the sun as always being south at noon, but it isn't. Sometimes the sun will arrive at the meridian, the southern point, before noon, and sometimes it will be after noon, and it can be quite a few minutes different, about 15 minutes one way or the other. So the east-west variation is not because of variations in the Earth's spin. The Earth's spin is essentially constant from day to day, but because it changes as we go around the sun, the speed at which we see the sun going across the sky will depend on the path of the Earth, and that's an ellipse. Hence, we get this variation which results in the analemma. So you can't rely on a sundial to tell you the time, because sometimes the sun arrives early and sometimes the sun arrives late at a particular point in the sky. So we can't use a sundial to measure how fast the Earth is rotating. So sundials do not work in that respect because the Earth's orbit around the sun is an ellipse. So it's nothing to do with the rate at which the Earth is spinning, it's purely the rate at which the Earth is orbiting the sun. So sundials don't tell us about the rotation of the Earth. If we want to work out how fast the Earth is spinning, we have to throw away sundials and find a much more accurate clock. So, what is a second? Well, since 1968, a second has had a very precise definition. It is precisely that many oscillations of a particular atom, called a cesium atom. Strictly speaking, it's a measurement of the frequency of the microwaves that result when that atom has an energy jump of its electrons from one state to another. But in effect, what we're saying is that that atom emits radiation at a particular frequency of about 9 gigahertz or so, and precisely that many oscillations define a second. So we're just hoping that all the cesium atoms in the world are stable, because if they're changing, then our definition of a second is changing as well. As far as we can tell, that is absolutely stable. How can we tell? Well, we can build different atomic clocks and they all agree with each other. So that tells us that all of these atoms are indeed stable. So this idea of defining a second by what an atom is doing is called the cesium standard. And there we see a 1960s version of a cesium clock. It doesn't look much like a clock. It's basically a way of keeping atoms and measuring this frequency of radiation that they absorb and emit. Now, the idea of atomic clocks is perhaps nothing particularly unusual for you. You know that that is a very accurate way of measuring time. Roughly speaking, an atomic clock ought to keep time to about a nanosecond, a billionth of a second per day. Or if you prefer, it would drift by about 1 second in 30 million years. And as I say, we can build lots of these atomic clocks. They are nominally identical. They can be positioned all over the world, and then they can be checked against each other to make sure they're not drifting. But we have phenomenal accuracy. And NASA is trying to make portable versions of these. It's actually made one that's basically not much bigger than the size of a toaster there. This box at the top of this particular satellite is an atomic clock, and this will allow any space probes that are either in Earth orbit or more likely space probes that are going out into the solar system. If you have an atomic clock on board, in principle you then have a very accurate timekeeper. It makes it easier to navigate with precision when you're on your way through the solar system. But even here on Earth, time absolutely matters. It's not just a question of if you're going to Jupiter, you need to know the time precisely. Here on Earth, it's rather important to know what the time is. We have, for instance, a network of GPS satellites orbiting the Earth every 12 hours or so. And the way we establish where exactly we are on the Earth is based on knowing how far we are from a handful of satellites. At any given instant, a few of these satellites will be above your horizon, and if you know how far away you are from these various satellites, you can work out precisely where you are on the surface of the Earth. How do you know how far you are from a satellite? Well, the signal from the satellite travels at the speed of light, so if you know the timing precisely, then you know your distance precisely, because the speed of light is a very well-defined quantity, approximately 300,000 kilometers per second. So there's an atomic clock on board each of the GPS satellites. But if any of those clocks were wrong, for instance, because we're dealing with converting time to distance and the speed of light, 300,000 kilometers per second, if a clock is wrong by a millisecond, that equates to getting a distance wrong by about 300 kilometers. Imagine your sat-nav with a precision of roughly 300 kilometers. It doesn't even necessarily put you in the right country. If the clocks were wrong by 1 microsecond, then you would still have an error of about 300 meters or so. It would put you in the right town, but it wouldn't necessarily put you in the right lane of the motorway or tell you which road you were going down. So if you want the precision of a GPS system to be accurate to a few meters, you can see that you need time accuracy of order nanoseconds. It's not a frivolous requirement, it's a necessity if you want the GPS system to work. And that effectively is what determines the accuracy with which you can place yourself at any point on the Earth, is the precision with which you can get the timing right. So every satellite has its own onboard clock, and those clocks should be good for quite a few days, or possibly even quite a few weeks. But just to be on the safe side, all the clocks are resynchronized, usually every few hours. In other words, they come above the horizon as seen by a ground station. The clocks are resynchronized every once in a while to keep the entire GPS network on the same time base so that we can get the precision down to a few meters. What can happen in a second? Well, quite a lot. Supercomputers these days can carry out a huge number of calculations a second. No, not 200 billion calculations a second. I've missed a few zeros off. No, still not right. That's it. That's the number of calculations that a supercomputer can do in 1 second. 200,000 million calculations per second. That's what you can do with a large enough rack of computers. And even if you have that computing power, if you want to run, for instance, a simulation of how the early universe evolved into the universe that we see today, a typical simulation, astrophysical simulation of either the early universe or what happens when a star goes supernova, those simulations could take days or weeks or even months, even if you're running with that many calculations per second. So you can see these simulations require an enormous number of calculations. So what can happen in 1 second? Well, quadrillions of calculations on a given computer, and there are lots of computers like this in the world. We know that light travels at, in old money, 186,000 miles a second, or in new money, 300,000 kilometers per second. And even one of the fastest probes that we've ever made, Voyager 2, flying out of the solar system, is only doing so at about 16 kilometers per second. Fast for us, but tiny compared to the speed of light. If we come down to Earth and just remind ourselves again what can happen in 1 second, this is data taken from pre-COVID. Whether or not COVID would have made any difference, I don't know. But here's some statistics from 2019. In 1 second, across the world, approximately 300,000 texts were sent every second. 60,000 searches per second were carried out using a search engine such as Google. Other search engines are available. 75,000 videos were streamed each and every second of 2019. Most of those videos involved cats. Some of them probably didn't. 700,000 messages were sent per second using apps such as WhatsApp. Other apps are available. But one of the most astounding figures I came across was that in 1 second, you can expect 3 million emails to be flying across the world. And there's nothing special about that particular second in that particular year. You can quite imagine that all of those numbers were quite a bit higher, perhaps in 2020, 2021, and I haven't looked at the data for last year or this year to see what sort of numbers we're talking about. But that's just a reminder that an awful lot can happen in 1 second. But atomic clocks has been with us for a while, since the 1960s, and one of the things they've told us is that the Earth is slowing down. Only when we built atomic clocks did we have the ability to actually see variations in the rate of spin of the Earth. So back in 1968, when they set up the atomic standard, the cesium standard, they basically defined a second as being 86,400 of them make up what they call a day, i.e. how long it takes the Earth to rotate once on its axis. So in other words, a day was exactly 24 hours. But since then, the Earth's rotation rate has changed. And for quite a few decades, it was clear that the Earth was slowing down, to the point that the length of a day wasn't 86,400 seconds, but was 86,400 seconds plus a few extra milliseconds. The Earth was definitely taking longer to rotate once on its axis. Milliseconds might not sound much, but remember, if it's continuing to slow down, those milliseconds are all going to add up. So why is the Earth slowing down? Well, you have to do a little bit of history first. Some 4.5 billion years ago, it is thought that a Mars-sized object, usually called Theia, collided with the proto-Earth. So this is in the very early history of the solar system's creation. And basically, it looks like a large object hit the Earth, produced a huge spall of material, some of which later condensed to make our moon. And the rest of it effectively came back to the Earth, and the Earth reformed. So once the Earth had recovered from the shock of that impact, it was rotating approximately 1 revolution in 5 hours. Very fast spin rate compared to today. Who knows what the spin rate was before Theia struck it, because after that impact, any history of what the Earth was doing before the impact would have been completely wiped out. So the Earth was rotating very quickly billions of years ago compared to the 24 hours of today. So what is slowing the Earth down? In this little cartoon, we can see that the moon is raising tides on the Earth. Again, the tides have been exaggerated for clarity. So we've got a tidal bulge closest to the moon and one on the opposite side. And because the Earth is rotating, effectively it's dragging the ocean bulge with it, and that ocean bulge is no longer on the axis that defines the Earth-Moon axis. Because of the rotation of the Earth, the bulge produced by the moon pulling on the oceans is now rotated slightly because the Earth's rotation is effectively pulling it in that direction. So the bulge is slightly offset to the Earth-Moon distance, which means the moon is actually tugging a little bit on this bulge. It's tugging on that one a little bit more than this one, simply because it's closer. And so because that is ahead of the rotation, it's effectively pulling the Earth back. The Earth is trying to drag that bulge away from the moon, and the moon is putting the brakes on and pulling it back again. So effectively, what the moon is doing is slowing the Earth down. It's robbing the Earth of some of its angular momentum. Some of the spin of the Earth is being lost, and the moon is picking it up. That's why the moon is actually getting slightly further away from the Earth. The Earth is losing angular momentum, but the moon is gaining it. In physics, any closed system, the total angular momentum must be conserved, and so here it's a trade-off. One body is losing some angular momentum, the other one is gaining it. So the moon is moving away from us, and as I mentioned in the last talk, that meant that because the moon is moving away from us, eventually the moon will not be able to cover the sun in our sky, and we'll no longer have total solar eclipses. But the important thing here is that the Earth is slowing down because of the tidal effects of the moon. It's effectively a drag on the Earth system. So what? Who cares? The Earth is slowing down. Does that really matter? The day is no longer an exact number of seconds. It was in 1968, but since then it appears to have been a decimal number, 86,400 and a bit. Does that matter? Well, think of the analogy of what happens with the calendar. We have a year, which is not an exact number of days. we have a year which is approximately 365.2422 days. That's just if you look at the rate at which the Earth is spinning and how it's going around the sun, it just so happens that's the length of a year. If we didn't do anything about that, if we simply said our calendars are going to be 365 days long, then the calendar would drift with respect to the seasons, and we would have a problem if we left it long enough. So one solution is to say, well, we don't want our calendar to drift with respect to the seasons. We want January to always be in winter and July to always be in summer. So we're going to insert an extra day every 4th year, a leap day every leap year. And that would make the calendar year 365 1/4 days. Still not quite right. It's close, but it's still not quite right. If we introduce a second rule and say we're going to skip a leap day, if it's in a century year that's not divisible by 400, so the year 2000, for instance, was divisible by 400, so it was a leap year, but other century years will be skipped, then you get the length of a year to be 365.2425 days. That is very close to the actual year. So if you have this rule, add a leap day every 4th year and skip these centuries, then you get a very accurate way of keeping the calendar in sync with the seasons. That will be good for thousands of years before we have to worry about any drift between the two. But if we want to do the same with time rather than with dates, if we want our clocks to say synchronized with the rotation of the Earth, if we would like to say, well, it's 8 o'clock in the evening, so it ought to be dark, or it's midday, so it ought to be, the sun ought to be up there somewhere. If we want to keep our clocks synchronized with how the Earth is turning, then we need a similar concept for time. We need to add leap seconds if our clocks don't agree with the rotation of the Earth. Well, strictly speaking, we don't have to add leap seconds. We have a choice. We could just let it drift and say, to hell with it. The rotation of the Earth is changing, our clocks are getting out of sync with the rotation of the Earth, live with it. Alternatively, we could say, well, if the days are getting longer, let's just let the seconds get longer, so there's always 86,400 of them in a day. And that's one option, just let the seconds grow longer. But scientists would be furious because you'd have to keep adjusting the atomic clocks to run slower and slower and slower if the Earth continued to slow down. And we would have to effectively redefine the second continuously, rather than say this is a second, and when we're making a measurement, this is what we mean by a second. So that's not really viable as far as most scientists are concerned. So we have to come back with, okay, if we don't want drift and we don't want to let seconds get longer, we have to introduce leap seconds. This is what the rotation of the Earth has been doing for the last few decades. This is the length of the day after you've subtracted off 86,400 seconds. So this is the number of milliseconds that you're left with. It's only a tiny amount, but it's every day, remember? So back in the 60s or so, it was by definition 0, but you can see in the 70s, the day length got as much as 3 milliseconds longer. The Earth was definitely slowing down quite substantially back in the 60s and 70s. Then it speeded up again. Then it slowed down again. Then it speeded up again. Then it slowed down again. Trying to understand what the Earth is doing is part of the problem. Let's have a look at the actual graph itself in more detail. We can see that it looks rather noisy. Strictly speaking, it isn't noise. It goes up and down on a time scale, perhaps you can see that, time scale of yearly. So in other words, the length of the day actually gets longer and shorter depending on the season. This is not anything to do with the orbit around the sun. It's to do with the fact that northern summer, when the Earth is tilted towards the sun, means that the northern hemisphere gets warmer and the southern hemisphere gets colder, and vice versa at the other part of its orbit. It's nothing to do with distance from the sun. It's purely the fact that the Earth's tilt means that we get northern summers, southern winters, etc., and then vice versa. And by changing the amount of heat that hits the Earth, we're changing the atmospheric currents, which ultimately will affect other things as well. But you don't tend to think of the atmosphere as having much mass, and admittedly, the mass of the atmosphere isn't much compared to the mass of the crust, or the mass of the mantle, or the mass of the core of the Earth, but it is finite. And by changing the way air is circulating around the Earth, you do in fact change the rate of spin of the Earth. So this variation that we can see here is to do with known variations in the way the Earth's atmosphere behaves. But what about the big variation? If we ignore the fact that it seems to be rollicking up and down, some of the variation inside there that is not shown by that red line, some of that is earthquakes. When you have an earthquake, the crust of the Earth rearranges itself slightly. It might be a seabed goes up by 5 meters or something. Not much, but it's enough to actually change the rotation of the Earth. But when it comes to understanding why does it slow down, speed up, and why has it done so over the last 50 years or so, there is not a clear consensus as to why the Earth is doing that. You noticed I haven't shown the red line completely up to date. This is up to, I think, 2019 when I took this particular figure. It looks like the Earth is speeding up again, and it looks like we're heading perhaps back to being 24 hours again, despite the fact that we've spent quite a few decades going a bit more slowly. Some people hypothesize that this is to do with climate change. Ice caps and glaciers are melting, and it's not so much what the water is doing, it's what happens to the land when you melt a glacier. If you melt a glacier, there's less force pushing down on the land beneath it. The land might rise slightly, a sort of uplift, if you like, and that will change the rotation of the Earth. So Earth scientists are studying curves like this, trying to understand what is going on the Earth, or perhaps below the crust of the Earth, perhaps what's going on in the mantle that would explain why the Earth is going faster and slower. But the bottom line is, it's very difficult to predict. We can't tell what's going to happen next. It was a little surprise to find it's coming back to 24 hours again after 5 decades of being slower. Is it going to continue going faster, or is it going to change and go slower again? It's essentially impossible. It's even worse than the stock market. You can't predict what it's going to do next. So if you decide to add a leap second, how are you going to do that? With leap years, it's easy. If you want to add a leap day, we've got a formula. You count off, starting from a particular point, you count off, is it a leap year? If it is, you put an extra leap day in, and everybody agrees it should be the 29th of February. That's been universally agreed. That's what we're going to do. It doesn't really matter why. It's just that everybody agrees to do that. And we know that we're going to do that every 4th year, with the exception of century years, and we know that's going to be good for ages. But with leap seconds, it's almost impossible to predict what the Earth is going to do next. So how can we work out when the next leap second is due? Basically, we can't. The best we can do is to look retrospectively at what the Earth has been doing for the last year or two, and then figure out whether our clocks are drifting or not. And the leap seconds, whether we need one or not, is decided by the International Earth Rotation Service. Fantastic. I sometimes wonder what would happen if these guys go on strike. Would the Earth stop spinning? Presumably not, but their job is to look at the rotation of the Earth and decide, are we due for another leap second? Is the Earth slowing down to the point where we need another one? It is actually possible that if the Earth is speeding up over the last couple of years, it might not be impossible that we need to take a leap second out. We need to actually remove a second from our clocks rather than simply add a leap second. It'd be like removing a day from our calendar, something that we've never actually done. So the Earth Rotation Service will decide if we need a leap second and when it should be inserted. Leap seconds have been added since 1972. That's when the idea of trying to keep clocks synchronized with the Earth first came in. Leap seconds have been added at various points. Now we're looking at the right-hand scale here of seconds that have been added. Notice that leap seconds were added essentially every year during the 1970s and 80s. But because the Earth speeded up again, by the year 2000 and something, 2000 to 2010, in that period, it was close enough to 24 hours that we didn't actually need many leap seconds. So there was about a 5-year period where no leap seconds were added at all. And then the Earth slowed down again and more leap seconds were added. And a leap second hasn't been added since, I think it was 2018. Because, again, we're getting close enough to 24 hours that at the moment it doesn't look like we need a leap second. But if we did, what would it look like? Well, if you think about what clocks normally do at midnight, they go from 59:59, click, over to 0 for the start of the next day. If we decide that a leap second is required, every clock in the world has got to do something different. If you look at the last digit, 59:60, 0. In other words, 23:59:60 is a perfectly valid time. There are 61 seconds in that final minute if you decide to add a leap second. For us, you just say, okay, some minutes have got 61 seconds in them. Computers are not so resilient necessarily. If the programmer thought ahead, that might be fine. Some computer systems crash if you try and tell it there are 61 seconds in a minute at certain times. And then you have the problem of when do you insert this? Midnight makes a sensible, yeah, that's sort of sensible. Before you go to the next 00, you insert one. But which midnight? Greenwich midnight? But that's the middle of the day in Japan, or a different time of day for India or America. So you could say, well, everybody will put a leap second in at their own midnight. Well, you could if you wish, but if you don't put the leap second in at the same instant throughout the world, if you let everybody do it at their own local midnight, all clocks in the world will be out of sync by 1 second at some point during the day. And you say, well, who cares about 1 second? Remember, you can do 200 quadrillion calculations in 1 second. You can send 3 million emails in 1 second. So 1 second matters. In the case of finance, you might be moving $1 billion from one bank to another. It's quite important that you know what the time is to say, well, at this instant, the money is ours, but at that instant, the money is theirs. So banks do not want to muck about with leap seconds and not be sure whether the clocks they're sending them to are synchronized with the clocks where their money is sent from. So some people really don't like leap seconds because it has to be done ad hoc. You don't know when they're coming. People who program computers don't know whether or not there's going to be a leap second next year or the year after or the year after. It can only be worked out retrospectively. And so some computer systems and some computer programmers really do not like the idea of mucking about with clocks. Some companies really don't like leap seconds. For instance, Google do not want to have 61 seconds in the final minute of a given day. So Google have decided that they're going to do something different to everybody else. Instead of adding a leap second when they're supposed to, they have decided to avoid having that anomaly. They're going to add the second, not at the end of the day. They're going to add it a few microseconds at a time to every second during the day. In other words, they are going to deliberately run their clock slow by just enough such that by the time they get to the next midnight, they've made up that leap second. Not everybody does that, and that means Google's clocks are not the same as everybody else's clocks. Does it matter? It depends on what you're trying to do. Google have done this to try and synchronize all their clocks around the world, regardless of when a leap second might or might not get introduced. Some people say that's a great idea. Some people say, well, if they do it and nobody else does, surely that's a crazy idea. Imagine if you wanted to do the same with the 29th of February. Rather than add a few microseconds to every second and not put it in at the end of the day, what if you did that with February? Why do the clocks say it's 3 a.m.? Well, adding an extra day at the end of February causes too many glitches. Instead, we're going to run our clocks 3% slower during February, and then we don't have to add the 29th of February in at the end. So that's a joke in that it's just saying, what if we took the leap second smearing that Google have been doing and applied it to the calendar? It clearly doesn't work with the calendar. So leap day smearing is just a joke. But the problem of what are we going to do about leap seconds is by no means a joke. The International Telecommunication Union is a UN agency which was tasked with the job of figuring out what are we going to do with time signals for the next few years or the next few decades or the next century. Are we or are we not going to continue putting leap seconds in an ad hoc basis based on the calculation of what the Earth has been doing in the previous few years? We don't know whether the Earth is going to slow down or speed up in the next 5 years. Are we going to continue with this unsatisfactory state of affairs? They were asked to figure this out. In 2015, they made a monumental decision. They decided not to decide anything until 2023. They were procrastinating. I assume that sometime this year they will make a decision. Or perhaps they will say, well, actually, it looks like the Earth is speeding up again. So it looks like we're not going to need a leap second for at least a couple of years. So maybe we've got a little more time to figure it out. I am not too sure. I'm trying to keep an eye on what their decision is to see if they are going to come up with a decision to either eliminate leap seconds, to continue using them, or to just let clocks drift. So I've been telling you about what a second is, what can happen in 1 second, which is quite a lot in this modern digital age. I've been explaining why the Earth's rotation appeared to be slowing down, and we don't really understand why it's temporarily appearing to speed up again. We're not going to let seconds get longer. That's out of the question. But the question of whether or not we're going to continue with leap seconds is still, as yet, undecided. Thank you for listening.
Thank you.